Hi there, welcome back to the formulaic approach. Now today let us talk about carbon. We're going to talk about what carbon is, the properties of carbon, the unique properties of carbon actually, and the allotropes of carbon and some of their uses. Then of course the structure of these allotropes and some things that are not allotropes of carbon but are commonly confused as allotropes. Is that clear? All right. So now let's get into it now. What is carbon? Now, carbon is a chemical element that has 6 protons. So for which reason it is number 6 on the periodic table. It has 6 protons, 6 electrons. So and so for which reason it also has the electronic configuration 1s2, 2s2, 2p2. Okay, so and of course, seeing this, we also know therefore that if the octet electron configuration, octet rule electron configuration will be 2, 4, right? So what this tells you is that it has the capacity to either gain 2 electrons or give 4 electrons. So that is plus or minus 4. That will be the electron configuration, the valency, right? Now actually, what does carbon do when it wants to react? Now, carbon neither gains 4 electrons nor loses 4 electrons. Now, why is it so? Now, if carbon were to gain 4 electrons, the thing is that electrons are negatively charged, like you know here. So if it gained 4 electrons, it will become unstable because the electrons are negative charged, so negative charges will be too much. So it will become unstable. Think of phosphorylation of ATP, phosphorylation of an atom, for example, a molecule, sorry. For example, when you phosphorylate a molecule, what happens? In the biochemistry, we said when you phosphorylate a molecule, the molecule will do what? Become unstable. Why? Because the phosphate group that you're adding is highly negatively charged, has has many negative charges. So the same way too, if carbon were to gain 4 electrons, those are 4 negative charges, it's going to become unstable. So what if it were to give away the 4 electrons? Now, to give away 4 electrons require high amounts of energy, and that energy it doesn't want to give up. So what does carbon therefore do? Now, carbon engages in what is called covalent bonding. Covalent bonding. Now, this will lead us to the properties of carbon. So the unique properties of carbon are number 1, the tetravalency of carbon. Unique properties. So these properties are unique to carbon. It has tetravalency. It doesn't mean that there are no other elements in the periodic table that has some of this tetravalency. That have some of these properties, but these ones are borne by carbon. So tetravalency means that it has 4 valent electrons in the outermost shell, right? I'm going to show you how that is here when I want to explain something, a little bit about hybridization, but you should see my video on organic chemistry to understand it better. So tetravalency is just tetra, meaning 4, valency, that is, it has 4 electrons or 4 points with which to coordinate to another element or atom. So that's tetravalency. Another thing about the unique property of carbon is its catenation, its ability to catenate. Now, what does catenation mean? Catenation is just about its ability to, form carbon to carbon double or single bonds with itself and other atoms. So carbon can form long carbon to carbon chain. That's catenation. With itself, it can form long carbon to carbon chain to form a giant molecule. Do you understand? So that is catenation. It can also form those bonds with other atoms as well. So that is what we know as catenation. Then of course, carbon also has the property of forming stable, it forms stable covalent bond, like we said, stable covalent bond. All right. So these are the major properties there. The other one you could see is carbon is also, I'll remember when as I explained. So I have forms stable covalent bond. Now, what is the covalent bond? Now look at this, the word co. Co means together, right? Any word you have cooperate, coordinate, it means together. So covalent means sharing electrons, sharing their valence electrons. Is that clear? So that's what covalent bond means. All right. So now, if that's the case, now what are the types of covalent bond that it forms? And first, how does it even form it? Now, when carbon wants to react with other atoms, it becomes excited, right? We say it's in the excited state. Now, what does it do in the excited state? What it does is this. The atomic structure for this guy, 1s2, just shows an electron with two electrons with opposite spins here. For the 2s orbital, we have 2s2, so it means two electrons with opposite spins also. Then for the 2p orbital, now 2p, we have 2p2 actually, and we know that the p orbital is degenerate, that is split into three, which are the px, the py, and the pz. So it is 2px, 2py, 2pz. So since there are two electrons there, we use Hund's rule to fill. So Hund's rule said I should fill them in singly first before pairing. But we can't even pair here. Why? Because there are just two electrons there. Now, how is carbon able to be tetravalent? How is it able to form tetravalent bond? Now, this is how it achieves that process. Now, in the excited state, during the excited stage of carbon, during excitation, what does it do? It will promote, during excitation, there is promotion of an electron from this place to this place. Then you may ask, well, how is that possible? Well, how is the electron able to leave? Well, of course, because they are at the same energy level. Even though this P will be slightly higher than the S, we know that because they are at the same energy level, promotion is possible. So which means that the energy to go from here to here is not so much as the energy to go from energy level 1 to energy level 2. Exactly. They have the same energy level, so promotion of electron with that amount of energy, with little amount of energy, is possible. So it will promote an electron here, which now means that there are 4 deficient centers. Now this promotion leads to the formation of, I'll leave this guy, I'll just draw we now have a hybrid. Is that okay? So a hybrid that looks like this, we have the 2s2 and the 2p3 now. Exactly. So we now have 1, 1, 1 everywhere. So meaning that we now have 4 coordination points, 4 coordination centers that electrons can be added to for them to be stable. Exactly. 4 coordination points. All right. So it means that we can therefore have 3 types of covalent bonds, which are the sp3 covalent bond. Now, what is the sp3 covalent bond? That one occurs when we have 1 s character and 3 p characters. So that is 1 s here is merging with 3 p's in this place, and this is what we see first. Is that clear? So this one forms single bonds. Single bonds, as we will see in one of the allotropes that we'll talk about now. So for example, let me use methane as an example of a carbon atom, a carbon compound. So you see what looks like this. So you see that the carbon is able to form 4 bonds, 4 single bonds all around, right? To all hydrogens. What happens is just each of these hydrogen will come and donate their share electrons. Each of these hydrogens, they have only 1 electron, right? They have only 1 each of these hydrogen have one electron and they need to be complete. So this they need one more to be complete. So they will come and share the carbon. Our carbon has 1, 2, 3, 4, according to what we just did. So what it will do is it will bring its one. This guy, this is one hydrogen now. It will bring its one here. So by the time it gets here, then the one will join with this place so that this hydrogen has 2, the carbon has 2. Another hydrogen will come here, bring its own here. So this hydrogen has 2, the carbon has 2, or 1 more than before. Another hydrogen here, hydrogen having 2, another hydrogen here, this hydrogen has 2. So we now have 8 electrons, which completes the octet structure of carbon. And of course, you see that it's very small, it's tightly packed. Here's another property of this. So we said 1 is tetravalency, 2 is catenation, and 3 is ability to form covalent bond. Then the 4th one is that it has small atomic size. It has small atomic size. Hence, the reason why it can be tightly packed together when it forms these strong covalent bonds. Is that okay? So these single bonds you see here is called sigma bonds. They are called sigma bonds. Is that okay? They are called sigma bonds. All right. Now, so we know sp3 covalent bond. Now, if you want to understand more about it, I'll link a video in the description for you to watch that I've made on this. So now there's also sp2 covalent bond. sp2 covalent, once it's covalent, it means they are sharing electrons, right? So you see that in that case, each of them share electron with carbon. Carbon is also sharing their electrons. So these ones give rise to double bond, okay? Double bond. So in this place, we have carbon to carbon single bond. Here, we have carbon to carbon double bonds. Double bonds. So now this one is not sigma bonds alone. This one contains sigma and pi bond. Sigma bond and pi bonds. Is that correct? So we have carbon to carbon double bond. Then the implication of that is that this sigma bond is the strongest one, while the pi bond is weak. So the implication of that is that it will be weak. So the bond, so the whatever molecule is formed here is not going to be as strong as this one here. Do you understand now? That's the implication. Then we have the sp covalent bond. sp covalent bond forms triple bond. So we can call it triple covalent bond. Here we have 1 sigma, 1 pi. In this place we have 2 pi's and 1 sigma. 2 pi's, 1 sigma. So here we have carbon to carbon triple bond. So for this reason, this one forms a linear geometry with bond angle of angle on a straight line 180. This one forms a planar geometry. Planar geometry means a plane, okay? Bond angles between them is about 120 degrees. Then this one forms a tetrahedral geometry. Tetrahedral geometry with bond angle being about 109.5 degrees or 109 degrees 28 minutes. Exactly, 109 degrees 28 minutes. All right, so those are just the types of covalent bonds that you find in carbon. Now, what are now the types, the allotropes rather, of carbon? The allotropes of carbon. Now, you must first know what allotropy is. So we have 2 terms that students may tend to confuse. We have allotrope and we have allotropy. Also keep in mind that this is not isotope. Okay, so iso, similar type. Okay, isotope is just elements that have the same atomic number but different mass number, such as we have in magnesium. Which one do I remember now? There are many, okay. We have carbon 12 and carbon 14. Both of them are carbon-carbon because they have 6 protons, 6 protons. But look at the masses. The masses are different. Chlorine 37.5 and chlorine 35.5. Those are isotopes, okay? Now, what are now allotropes? So allotropes are substances that have allotropy. Let me start with allotropy. Allotropy is the phenomenon, the condition of being like this, of having allotropes. Allotropy is the condition of having allotropes. Now, what does allotropy actually mean in reason? Allotropy means the existence of the same substance in different physical states. So carbon is carbon, but in physical states we see it exists in diamond, exists as diamond. We see it exists as graphite, and we see it exists as fullerenes. Okay, I'll be using just one common type of fullerene here, the buckyball. My only example is the buckyball because that's what I know about. Okay, or Buckminster ball, Buckminster fullerene. All right, I wanted to say, okay, so these are the allotropes, the different forms in which that carbon exists. So, for example, if I say, let me use Christianity, for example. So, God exists as spirit and exists as, so we have God, Father, Son, Holy Spirit. So we have the God, the Father, then we have the Son that existed as human, then Holy Spirit, which is spirit that we cannot see. So you see those forms still represent the same thing, but in different forms, right? So carbon, allotropy, allotropy is the existence of a substance such as carbon in different forms, in the same physical state, the same state that you can see. You can see all of this, but there are different forms of this, of the same thing. There are different forms of the same thing. But I'll now mention some things, so stick to the end, because I'll mention some things that you commonly confuse as allotropes. Is that okay? All right. Now, let's talk about, now these are pure allotropes. Is that okay? These are pure allotropes of carbon, pure allotropes. Now, let's talk about diamond quickly. So based on what I have explained here, diamond, for example, you know that diamond, at least you should know that diamond is the hardest substance in the universe, right? Okay, diamonds are the hardest substance in the universe. Nothing breaks diamond, do you understand, except my bones. Exactly. So diamond is the, apart from my bone, diamond is the hardest substance in the universe. Exactly. All right. But that was just a joke though. Diamond is the hardest, okay? The hardest substance in the universe. All right. So now why is it hard? The reason is because it has throughout the entire molecule of carbon, it forms covalent, strong covalent bonds. So in the atomic scale inside the diamond, what you see is a tetrahedral geometry of each of the carbon atoms. Is that clear? But outside, the shape you see with a diamond is actually octahedral. So you should not confuse this. Each carbon in a diamond is bonded. So if I say this is a carbon here, this is a carbon here, there will be a carbon here. So you have something like this, like this. You see this? So there is a bond angle of 109 degrees about every of this carbon. So there is a carbon here, there is a carbon here. So this one here is bonded to another, forms another tetrahedral geometry with another carbon. Do you understand now? Forms tetrahedral geometry. But at the end of the day, when you see the structure of the guy, each carbon is bonded to four other carbon atoms. Exactly. So I'm not showing this in full because some we have to come out. So it has a 3D geometry, three-dimensional geometry. So that's why in the outside, on the outside of carbon of diamond, then you say that we have a structure that is octahedral. But inside, what you see with each of the carbon is what? tetrahedral geometry because each of these carbons are sp3 hybridized. Each carbon is what? sp3 hybridized. So they form a structure that looks a little bit of weird, you know. Each one will be bonded like that, like that, like that. So that's typically it. So the point is this: we usually draw a structure that just looks like this, using a wedge bond here and a dashed bond at the back. A dashed bond. This dashed bond shows you that it's at the back, and there's another one. So this one is coming out of the board. This one is going into the board. So there's around them we have 109.5 degrees. That is the farthest away, since you know Vespa theorem. And if you want me to release video on Vespa theorem, just put it in the comment section. I'm going to talk about it. So that's about diamond. So I also said that it has that shape. So then someone might ask that why is it that, so if a diamond is the strongest substance, then how are you able to obtain one small diamond? How are we able to obtain a small diamond? Apart from cutting, like you might be thinking that in nature we don't see a molecule that is, we don't see a structure that is endless, right? Since I just said now that the entire carbon to carbon molecule is, covalently bonded to another carbon, very strong covalent bond throughout the entire length of the thing. But in nature, we see carbon exists in different shapes. So what makes those shapes, what broke them apart? I don't know if you understand what I'm trying to say. Okay. Now the thing is, in the natural state of formation of carbon, there are impurities, okay, that might form. So those impurities will create, so inside the carbon we have intramolecular forces. So those intramolecular forces are the covalent bonds, exactly. But during the natural process of forming carbon, their impurities might come in. Is that okay? So those impurities will create intermolecular forces that are quite weaker than these covalent bonds within the carbon. Exactly. So because of that, those covalent bonds are broken by different natural processes, and then you now have different sizes of carbon, of diamond, in the places we find them. Exactly. All right. So that's what makes them broken into different this thing naturally, different sizes naturally. So that is carbon, that is diamond. Then what are the uses of diamond? We use it to cut other things because it's the hardest substance that I said is the hardest substance, no, except my bone. Then my other disease over there. Okay, so we use it to cut. We also use it for, so it has fundamental properties such as hardness, hardest substance known, lustrous. It's also lustrous because it allows light to pass through it. It allows light to pass through it. So because of that, it's lustrous, shining. Is that okay? It's shining. And then it has high what again? Diamond. Hard, lustrous. Okay, so when I remember all the things, I'm going to tell you. Then non-conductor, it does not conduct electricity. It's a non-conductor. Now, why does it not conduct electricity? Because it has no free electrons. There are no free electrons. So since there are no free or mobile electrons, diamond does not conduct electricity. If I remember any other property I've mentioned. Then let's talk about graphite. So all of the carbons in diamond have established the fact that they are sp3 hybridized. Now what is now graphite? How about graphite? Now graphite is another type of allotrope of carbon, another allotrope of carbon. Now graphite is a little bit different from diamond in the sense that graphite is made up of sp2 hybridized carbons, sp2 hybridized, sp2 covalent bonds. I don't want to use hybridization here, is that okay? but it's the same. It's pretty much the same. That is the term. It was the term hybridization that Pauling used to explain the way carbon behaved. So Pauling was the one who used it to explain it. I think in 19 whatever. So sp2 covalent bond is what we find in these guys, okay? And the shape that they form is hexagonal shape, and they have weak bonds around them. Let me show you the structure of the hexagonal shape. So you have a carbon here, a carbon here. Let me show you using something like this: a carbon here, a carbon here, a carbon here, a carbon here. Okay, so this carbon again will be bonded to another carbon. This one will be bonded to another carbon, another carbon, another carbon, another carbon, like that. So this one will be bonded to another carbon, another carbon. You see that the molecule is planar, right? It has a planar geometry. So planar geometry. Okay, planar geometry. Only that, because it's a solid, it will not be a flat plane. Now, so it means that these guys now arrange themselves in a way that make them solid, right? So how do they now arrange themselves? We now have weak intermolecular forces now between the carbons. So they are layered. They are layered. Now, the forces of attraction between each carbon in a layer is covalent bond, right? Weak covalent bond because we have sp2 hybridized carbon here, double bonds in places here. Is that clear? So I said they now form themselves in layers. So this plane will be on another layer of carbon to carbon to carbon to carbon to carbon to carbon to carbon. This one, so like that. So this one is above, this one is below. Is that clear? So this thing now, if I flatten it, then I have another layer here. So in between them, we now have van der Waals forces. And what do you know of van der Waals forces? Van der Waals forces are very weak forces of attraction, right? We call them London dispersion forces. London dispersion forces. So van der Waals van der Waals forces are what put the layers together, and so that's why it's easy to break the layers. And the presence of double bonds shows that there will be, because of these bondings that you have here, it shows that there will be delocalized electrons. So there's presence of what? Delocalized electrons. For which reason this guy can conduct electricity. So this guy is what? A conductor. It can conduct electricity. And that's why we use it as an electrode in the electrolytic process. An electrode. If you want me to release video on electrochemicals, I'm planning, by the grace of God, to release a series, not series, like in one video, I will explain everything on electricity. So if you want me to do that, you can let me know in the comment section quickly. So I said it's used as an electrode because it can conduct electricity, since it has the localized electron for the presence of double bonds, pi, and the pi bond I said is weak, right? All right. So that the localized electron can conduct electricity. It's used as electrode. It's also used in pencil, right? We use it in pencil. Okay, so, and then it is for this reason, because there are weak forces here, it is more like soft to touch. Okay, so the layers usually can move over each other. They can slide over each other. Do you understand? So there are weak forces holding these guys, this layer together. All right. So now, how about fullerenes? Now, you see, fullerenes are now quite different. Now, fullerenes are also sp2 hybridized. Fullerenes are also sp2 hybridized. So let me use the example C6C. That's the Buckminster fullerene. Buckminster fullerene. commonly known as C60, sorry. So this guy has so many uses, right? First, what is the shape like? So we have seen football before, which of course I'm sure you have seen. Okay, so you see things that look, shapes that look like this. So you see shapes that look like this. Yeah, like this. Shapes that look like this. Overall, you will notice we have, I wanted to draw this into, that's what I was looking for. So what are you noticing? You notice that we have hexagonal shape here, and we have this hexagonal, this is also hexagonal. Then we have pentagonal shapes here, right? So you see, if I continue this thing to form what looks like a ball, right? Yes. So that's the Buckminster fullerene. Now it has double bonds in certain places. Exactly, it has double bonds. So so what does that mean? It also means that this guy is going to have delocalized electrons. Okay, so the shape looks something like this, and it is also unstable, just like this guy is not like unstable. It's not unstable, as in it is like it's not as strong as the diamond. Like we said, graphite is also not as strong as diamond. Of course, by experiments has also been found by that if you heat up, you can form artificial diamond from graphite by heating it up to a very high temperature, very high, ridiculously high temperature. So delocalized electrons are also on these guys, and it has pentagonal shapes and hexagonal shapes that form a hollow. They form a hollow shape. They form a hollow that is like a round ball, and that's one of the reasons why it has its use in nanotechnology. So it has its use in nanotechnology. I'm going to tell you what we use. Two of the uses that I think I know in medicine and electronics. Okay, so to recap the things I've talked about, so this is also going to be a conductor, right? It's also going to be a conductor. The geometry is also sp2 hybridized. It's also sp2 hybridized carbon. But there are some carbons there that will be sp. Yeah, they're all sp2s. So they are sp2 hybridized carbons, sp2 covalent bonds. Okay, and I'm trying to make sure that I talked about everything that I said with these guys here. So this one forms a hollow, right? Like a ball, right? Good. So that's one of the use why it has found its use in nanotechnology. So nano encapsulated drugs, they use fullerenes. The Buckminster fullerene, for example, they use it for nano encapsulated drugs. They will what it does is that, number one, know that this external surface of the ball can react with molecules. So it means that it can hold molecules on it, right? Good. Then inside also can hold molecules. So it means that it can be used to encapsulate something to kind of protect it in a way and get it to enter into the cell of the host or of the thing of the organism in which it's being administered to. Exactly. So Buckminster, that guy is used in nanotech that way for medicine, especially the administering of drugs. They use for drugs delivery into a cell, all right? Then in electronics, it is used in for, I think, semiconductors, right? Is this for semiconductors? Is this for semiconductors because it requires some energy to actually cause it to conduct as well. So that's basically it. That's basically it. All right. So now, what are the things that are commonly confused as allotropes that are actually not considered allotropes of carbon? Okay, they are just they are just carbons that exist naturally that can, that can be converted from one form to another. Listen to me, look at this. So I use a mnemonic: women, white people like or love being adored. White people love being adored. The white stands for wood. People stands for peat. L stands for lignite. Bean stands for bituminous coal, yes. Then adored stands for anthracite. Now you see, this order is very important because in your textbooks it might not be listed this way, okay? But this order is very important because that's how I like to explain it, okay? So for wood contains about 50% carbon. Is that okay? Approximately 50% carbon. Approximately 50% carbon. So by the time you compress wood, so wood is not particularly an allotrope of carbon, but a different form in which this guy exists. The substances that contain it, okay? So adored carefully, because at the end of the day, it will form charcoal. Now I wanted to say this. So I answered that peat, if you compress wood, heat it up, you are going to get peat, which is about 60%, 60 to 70%, I think. 60 to 70% carbon. Okay, so you see that the carbon content is increasing with the heat, right? You heat it further and keep for a very long time. To convert wood to peat, exactly, it has to be compressed for a long period of time. So to get lignite, you also do the compression process further. You compress peat and heat it up. You're going to get 70 to 85%. 70 to 85% carbon is bituminous coal. 70 to 85% carbon. So for here, it's just approximately 60% carbon. So that here will be 60 to 70% carbon. Okay? So that anthracite is the one that has about 90 to 95% carbon. All right. Then charcoal is principally carbon. Exactly. Now, and there are different types of charcoal, but I don't want to get into that now. So the point is that as you increase the temperature also, and over a very long period of time, for example, to form anthracite, to form bituminous coal, it has to have the guy has to have been compressed or kept under the earth through. Now the process of transformation of this is called coalification. Exactly, it's called coalification. Okay, so through coalification occurs over thousands to millions of years. Exactly. Right. So the process by which all of these are formed. Yes, and we are qualifying wood. Exactly. So it takes very long period of time. So that'll be it for this video. Is there anything I didn't cover? No. Of course, I did not cover types of charcoal, animal, wood, etc. charcoal. This wood charcoal I talked about here. But in further video, maybe I will now talk about carbon fully. Okay, I will just, here I just want to talk about the allotropes. And so God bless you as you subscribe to the channel and share the video with your friend. Also click the bell notification to get notified whenever I drop a new video. God bless you.